Yeah. Good morning, my dear students. Good morning. Good morning to all of you. Oh, nice to meet you on online. Okay. Hope my audio and video are all clear to you. Okay. Because I have started this class. I am handling this class from our department. Okay. Just so I got the internet connectivity. So I am handling the class from my our department. Okay. Morning class I took from home. So this hour I am handling from here. So okay, good. So I will share the today's this one material to you. Right? Yeah, this is a PPT. Just is the PPT is clear? Yeah, it's clear. I think. Okay. Is it clear to all of you? Musikiran?
Yes, sir, it's clear.
It's clear. No, whether only no. Actually, PPT alone clear or whether all others windows comes, only PPT alone comes. PPT alone comes, no? I think so. Actually, yeah, no. Even if I minimize, only the PPT cannot be minimized. It's come full screen, no. It's okay. So last class we have discussed the Indian seismic codes, no? Like the good structural configuration, lateral strength, adequate stiffness, good ductility. These aspects, the IS code, seismic codes cover all these aspects. I told you in the last class. This was the last slide I discussed with you. Okay. And how that's first Indian IS 18 in the earthquake seismic codes in India, namely IS 1893 was published in 1962 first. Okay. And then IS 1893 part 1, 2002 is revised. That was the 5th revision. Okay. And in the recent past, 2016 also, this IS 1893 part 1 has been revised. Okay. Then what are the other codes in earthquake engineering? If you see, the last class I told you, IS 4326 1993, earthquake resistant design and construction of buildings. Okay. IS 13827 1993, which is Indian standard guidelines for improving earthquake resistance of earthen buildings. IS 13828 1993, Indian standard guidelines for improving earthquake resistance of low strength masonry buildings. And IS 13920 1993, actually this has been revised recently in 2016. Okay, Indian standard code of practice for ductility detailing of reinforced concrete structures subject to seismic forces. So this IS 3920 and IS what is that 1893 is all very important for you. Okay, IS 3935 1993, Indian standard guidelines for repair and seismic strengthening of buildings. Okay, and also I told you because after the Bhuj and Clary earthquake, Clary and Latur earthquake of Maharashtra. 1993, which occurred on September 30th of 1993, which I experienced. That time I was staying in Regional Engineering College, Warangal. Is there any latecomer? Something is coming. Let me to check. Yeah, I have to admit. Yeah, it's okay. Right. That time I was staying in REC Warangal. I told you no that I experienced. Afterwards, all this IS code have been developed under the chairmanship of Professor A. Sari of IIT Kanpur. Sorry, IIT Roorkee. Okay, right. Let's see. There are 1893, 1984. Afterwards, it has been revised in 2002. PTA for earthquake design. So this write-up talks about the very the code of provision, but that's not important. That's skip. Okay. In the IS 1893, there are 5 parts. Part 1 is for general provision and buildings. Part 2 for liquid retaining tanks, elevated and ground supported. Part 3 for bridges and retaining walls. Part 4 for industrial structures, including stack-like structure. Okay, and then part 5 for dams and embankments. But you will be using only part 1, general provisions and buildings. That I use code alone for you during exam. The other codes are not necessary for this subject. Okay, right, very good. So this PPT seismic evaluation network. Okay, this is not necessary for you. Okay, this PPT is already over. I will go to another PPT for you, right? Since this PPT is over for you, I will go to another PPT. Let us see. I will skip many things which we have discussed already. Okay, so in this PPT, I will skip many things which we have already discussed. Let us see whether anything to be discussed. Just I will have a look at the shear wall in a building. How the shear walls are being provided in a building. Just have a look. Okay, so the shear wall in this building frame. Here shear wall is introduced, here introduced, here introduced. here introduced. Okay, thus they are a lateral load resisting system. Lateral load resisting system. It resists shear, base shear, and shear at every level. Okay, when the building some people design lateral loads. Lateral loads due to earthquake. Okay, so see, have a look how the shear walls are being provided in the building frame. Okay, any manner it can be, any fashion can be provided, and you have to examine whether it provides adequate resistance or not. It's just to give you some awareness from earthquake tips. Just I am showing. Okay, shear wall will look like this Z shape, L shape, like this. Okay, shear wall in RC buildings, different geometries are possible, right? Hollow core and around elevator also. Lift core you are putting over lift that core also can act as a shear wall. Okay, RC hollow core around the elevators, right? So here, okay, this I think I will just escape. This is sliding bearings, base isolation. Okay, base isolation, rollers, and then rubber bearing. Here rollers. Okay, any hand tool possible here? No, it's okay. Rollers, and then this rubber bearing, and elastomeric rubber, net core elastomeric rubber bearing here. Okay, this and all, just you can have a look. All these things are available in the earthquake tips. The link already I mailed it to you. I have sent it to you. Okay, the link is already mailed. You can download these tips and go through this earthquake tips. So here they are called adaptive system. Okay, response control. Okay, they comes under response control. We will discuss them in detail. Already told you that response control, how to reduce the response of the structure. Okay, for which in a building frame there are braces, visco dampers are provided like this, right? And friction damper. How the friction damper look like? Just have a look. How visco fluid damper is being provided as a diagonal of a building frame. Okay, how friction damper is being provided in the X frame. Okay, X braces, X braces. How these K braces, they are called K braces, this is called X braces. How yield dampers are provided as metal dampers. Yield damper or metal damper are being provided as K braces. Just you can have a look at the earthquake tips. The details are available. You can go through later. So now I want to show certain significant earthquake of the world. The time history. The time history. In other words, signature of certain important earthquake. This is called the El Centro earthquake of May 18, 1940. Okay. At the time we didn't have seismograph to record its signature, but later it was guessed and this signature obtained in the algorithm. The algorithm, a program of experts have developed this kind of El Centro earthquake signature like this from its known intensities. Okay, they arrived at the signature in a web program, in a simulation. In a simulation they obtained it. Okay. Just the other famous signature of the earthquake, Konya earthquake of 1967, and then Kobe earthquake of 1995. Okay, so these signatures are widely used. They are called time histories. Okay, time histories. Okay, then the time domain. See, they are called time histories, time domain. The apsis are the time is taken more, time in seconds. So time domain. They are in the time domain. So that is why they are called a time history. The signature is called time history. Okay, time history. So we also do time history analysis. No, with that time we feed this data, this signature we are feeding the simulation, the software simulation. Let us see. I will look at the other famous this one. Okay, I have shown all this El Centro. See here I have shown El Centro, Parkfield, this one, San Fernando. Okay, San Francisco earthquake, old one. Likewise, famous earthquakes signatures are which are widely used all over the world for time history analysis purposes are shown here. Okay, just we have a look, right? Which I collected from various sources. Now I want to tell you. See, I thought out starting you significance of ductility. That I will start after the discussion. I will just start a letter. Concept of response spectrum, right? This one I want to tell you because you don't have a subject structural dynamics now. Strictly speaking, you are supposed to study structural dynamics first. After having studied structural dynamics subject, you have to study next the seismic analysis of structural subject. That is the order. Okay, in this order only you have to read this study the subjects. But I already pointed out in our college curriculum, but the person concerned have not taken into consideration properly. First 2 years they have taken. I pointed out the anomaly in the curriculum. It was taken care. So parallelly they offered structural dynamics also elective. So structural dynamics and seismic resistant design you have studied parallelly. But this time that anomaly has happened. I am not responsible for it. Already I pointed out this one to your coordinator. Okay, without studying, it's not appropriate to teach you seismic resistant design without teaching you structural dynamics. Okay, it is a wrong order. This semester you are studying seismic resistance of structures. Next semester you are going to study structural dynamics. That is wrong. I will tell you. Experts, if any experts happen to see your mark list, they will understand. Okay, the anomaly existing, they will understand. But I pointed out several times with the department. In spite of that, they are doing it now. Why I should again point out? That's why I'm keeping quiet. Okay, already conveyed. They are least bothered about it. When the people concerned are least bothered, why I should? Okay, let us say okay. Now, because concept or response spectrum, you will be learning in structural dynamics subject. Okay, but however, I will brief here. Why I do brief here? Because I am going to use response spectrum. A seismic coefficient method I am going to teach you. In seismic coefficient method, I have to teach you what is meant by response spectrum. That is why I want to discuss it with you now, right? See, I have a oscillator, right? This is called oscillator. A single degree oscillator. Single degree. There are multi-degree and single degree. Single degree means, for example, you take a water tank, elevated water tank. Okay, the stage is the stage on which the water tank is supported. The masses, just to imagine, they are lumped at the water tank level. Okay, at the water tank level, the masses are lumped, including the mass of the even the stage, everything lumped there. In the stage, the stage of the water tank, stage means column and braces, braced beams are there. No, that is called stage. Say that stage is lateral stiffness. We are taking it here. Okay, the stiffness of this member, lateral stiffness of this member. K, say, with the mass M is lumped here. Okay, so it is a single degree oscillator called a single degree freedom system. Okay, what is single degree freedom system? What is multi-degree freedom system? And all you will be learning in the structural dynamics subject. Okay, so in this I have a single degree oscillator, right, of known damping value. Sir, what is mean by damping? Don't ask me now. Just take it as like that. Damping. What I am doing, I am giving a time history here at the base. At the base of the single degree oscillator with a particular stiffness and mass and a particular damping. Okay, I am giving say 5% damping. I am giving a time history. I just now shown you several time history. No, all over the world used the earthquake accelerogram. That is also called earthquake accelerogram. Time history. I am giving. Okay, acceleration. Time versus acceleration plot. Those are this one. Okay, they are all accelerogram. Okay, so the time history I am giving here at the base. Now this single degree oscillator oscillates. Okay, its response also I am recording another time history. Response of the structure. Okay. Likewise, what I am going to do, I am changing its time period. First Tn1, T suffix N1. That is the notation used. T suffix N1. Okay, so a particular time, a particular period, right? Again, I am changing its period. Again, I am giving the same time history and recording its response. Again, I am changing its period. How do I change its period? By changing its stiffness and mass of this single degree oscillator. I can change its period Tn1, Tn2, Tn3, Tn4, like that. I am changing its natural period. Okay, and then I am giving the same time history. I am recording the response of the single degree oscillator. Now, what I am going to do? I am going to do a plot, which is frequency domain. Frequency domain means here I have not taken frequency. I have taken time period. Inverse of frequency is period. Okay, so time period. So the time period domain. Instead of saying frequency domain, I would say time period domain. So in the abscess, I am going to take time period. Okay, in y-axis, I am going to take its maximum trace oscillation here. In the response, I am getting acceleration. No, the maximum oscillation. I am going to take here. Okay, so okay, no problem. Now see, this way we are plotting. See here, the natural period of vibration is again is taken, right, of the single degree oscillator, and the average acceleration coefficient is means it's SA by G value. That is in terms of this maximum trace acceleration. See here, in that response of whatever maximum acceleration I am getting, that I want to express in terms of acceleration due to gravity. For that, what I am going to do, I am going to divide it by acceleration due to gravity. If suppose I am getting 1g acceleration here, say, g, I am getting the maximum acceleration says g. It means g divided by g, 1. If I say that acceleration coefficient is 1, means 1g, okay? So I always fraction, 0.5g, 0.6g, in terms of g I want to express. That is why it is called acceleration coefficient, average acceleration coefficient, SA by G value. 0.1, 0.2 means 0.1 means 0.1 times G. 0.2 means 0.2 times G. 0.3 means 0.3 times G. 0.7 means 0.7 times G. Okay, SA by G value. So the maximum trace acceleration is the maximum acceleration. Maximum trace acceleration is within 0.7 G times acceleration due to gravity. See, different curves are there for 20% damping, for 0% damping, 2% damping, 5% damping, 10% damping, 20% damping. Damping is possible up to 20%, and which no, only the maximum is 20%. Okay, different damping, the curve is drawn, developed. Average acceleration spectrum name. Okay, I will read out response spectrum. It's called response spectrum. A response spectrum is defined as a curve. Please, all of you here. A response spectrum is defined as a curve which shows the peak response of a single degree freedom oscillator, which shows the peak response of a single degree freedom oscillator having a certain damping. Having certain damping means 5% damping to a given input ground motion. To a given input ground motion. The input ground motion is the known, well-known time histories, signatures of well-known earthquake we are giving. Figure shows the average response spectrum suggested by G.W. Hausner. It shows the variation between peak acceleration as a function of acceleration due to gravity. It shows the variation between peak acceleration as a function of acceleration due to gravity. That's why we are taking SA by G. Instead of putting only S of peak ground acceleration, peak acceleration observed, okay? Maximum trace acceleration is taken on the y-axis and the natural period on the x-axis. Natural period T is on the x-axis. This is suggested for design purpose after a study of response of 4 strongest earthquakes that have occurred in the USA. Okay, this is the explanation for response spectrum. These notes I will give you later. Don't worry. Okay. Now we are just going to smoothen this curve. Idealize. We are slightly going to idealize this curve. See, the response is inclined closer to the y-ordinate, and then it is going to be flat for some time. Okay, just flat, and then it will be exponentially, it will be decaying like this. Okay, so finally this one is this one. See, concept of response spectrum. This is a response spectrum incorporated in our IS code, in our ND93. ND93, this is the response spectrum. SA by G value is given. Please see here 0, 0.5, 1, 1.5, 2, 2.5, up to 2.5. 2.5 means 2.5 times acceleration due to gravity. SA is equal to 2.5 G. SA by G value is 2.5 means SA is equal to 2.5 into G. 2.5 times acceleration due to gravity. Okay, the color shows the rock or hard soil. The single degree accelerator is this is how it is fixed. It is on rock soil, medium soil, soft soil. Okay, so when you design the buildings, you have to take into account the soil in which it is resting, either medium soil or soft soil, rock soil. Accordingly, you have to refer the curve. Okay, and also there are empirical formula available to compute the natural period of any building frame. Okay, normally the natural period will lie anywhere between this one, 0.2 seconds to within 1 second only. Most of the buildings, we deal with the medium story building, G+3, G+4, G+5, likewise G plus 2, G plus 3, G plus 4, G plus 5. Likewise, only medium story building only mostly we are dealing. Okay, our apartment building, residential buildings and all. That is why if you compute its natural period using the available empirical formula, normally its natural period lies somewhere between 0.2 seconds to well within 1 second. In such case, see, it attracts more severe forces. The SA by G value comes around 2.5. It means its natural period falls well within the attracting more earthquake forces. Suppose the structure is a long period structure, for example, chimney or transmission line tower, whose time period is long. Okay, for one oscillation, when it vibrates, for one oscillation, it takes maybe 1.8 seconds or 2 seconds or 2.2 seconds means, see here, suppose it is 1.7 seconds, say 1.77, just on medium I'll say. See, that drastically the SA by G value comes to only 0.75. Okay, SA by G value comes to only 0.75. So it attracts only less severe earthquake forces, right? So it is not vulnerable. Long period structures are not vulnerable to earthquake. You take still long period structure like a very tall chimney, even tall structure. Many tall buildings are constructed abroad. No, tall structure, 50 story, 100 story, 150 story. Such a tall buildings you take. Buildings which are more than 150 meter heights are classified as tall buildings abroad. Okay, as per foreign code, as per the foreign code of practice, many buildings which are above 150 meter height. Okay, 150 meter height now, how much stories you see? Each story say take it as 3 meter. Then for 150 story, how many stories? More than 50 stories. See, right? Such buildings are treated as tall buildings as per their code. But in India, we cannot construct such a tall building. No. But in our IS code classifies what is tall building, what is multi-story building. Buildings which are above 45 meter height or 50 meter height are classified as tall buildings in India. Buildings which are below 50 meter height are classified as multi-story buildings in India. Okay. So that is the classification as per our IS, our code. It's okay. But keep it in mind, tall buildings are not vulnerable to earthquake. Why? Its time period is very high. Say some 3 seconds time period. It is resting on medium soil or rocky soil. It attracts only less severe force. The SA by G value comes very less. Okay, so it will be subjected to design lateral loads less. But the medium-rise buildings, our multi-story medium-rise buildings, time period fall well within somewhere 0.1 seconds to 1 second. Okay, so they are going to attract more severe forces because its SA by G value comes 2.5 G. Okay, SA by G is 2.5. SA is 2.5 G. So SA by G is 2.5. Okay, it means it attracts more severe forces. So the design lateral loads, it will be subjected more. Okay, more design lateral, the magnitude of design lateral loads to which it is subjected during earthquake. It means horizontal forces which are likely to act on the structure when it is subject to earthquake is going to be very high. Okay, so that is the meaning of this concept of response spectrum. We are using it in our design, right? The same plot. Just now I showed you, this plot. The same plot is given here. Okay, for different damping, and they are idealized. This is again once again I am showing a response spectrum for rock and soil sites for 5% damping. This is the response spectrum we used in our IS code. One small modification, small changes. Please, all of you see here. What happened? IS 1893, 2002, isn't it? In 1984 and then 2002, in the both revision, this is the response spectrum followed. For either in IS 1893, 1984, the method was called seismic coefficient method. Seismic coefficient method, computation of design lateral loads. That method is called a seismic coefficient method. But in IS 1893, 2002, they have changed that name into equivalent static force procedure. Not a seismic coefficient method, equivalent static force procedure. computation of equivalent static force. Otherwise, equivalent static force procedure. That name they said, they removed that name, seismic coefficient method, that name was removed. Okay, the same response spectrum adopted as shown here. But IEC 1893, 2016, what they have done to calculate the design lateral loads by equivalent static force procedure, the response spectrum, small modification they have done. What that modification now? What the experts have done? This curve is there, no, this part of the curve, which is closer to the ordinate. They merged it with this ordinate, with y-axis. This is merged with y-axis. So now know this gap. Okay. So this flat portion start here itself. The flat portion start here itself. Even the natural period of the building is 0.05 or 0.01, very closer to this one. Here the value is, suppose the building, say here, suppose this is 0.5, this is 0.25, say 0.1. Actually, the natural period of the building is 0.1 now. Normally, what you will take, you will take this value. Now, this curve is made flat here. So, in such a case also, they say by G value is going to be 2.5. So, this is made flat, okay, in the recent code. All others are same. That is our modification. But please keep it in mind. This is for equivalent static force procedure. For response spectrum method, is another method of computing design lateral loads. Okay, by doing eigenvalue analysis, by computing its more shapes and more vectors of building frame. Okay, that to calculate, to refer the response spectrum, this is a response spectrum they retained. The same response spectrum in this portion. This response spectrum they retained as it is. Only for seismic coefficient method, equivalent static force procedure, this curve is modified flat. So totally 2 response spectrum suggested in our IS 1893 2016. Okay, with the flat portion, with without this inclined portion, fully flat here. That is for equivalent static force procedure. And then this same whatever available here, whatever you see here, this spectrum for to compute design lateral loads by response spectrum method. Okay, so 2 curves they have adopted. That is the only change. That the code is not there. Calculation of seismic forces. Okay, this we will see while working out problem. Next class I will be working out a problem. I will be seeing this how to compute design lateral loads by equivalent static force procedure. That time I will teach you this. Okay, because to explain you what is response spectrum, I brought this PPT. Please, all of you see, I am uncomfortable in teaching you the seismic resistive design of structures because you are not studied structural dynamics. It is a wrong order. Okay, when the structural engineering program was started, okay, the curriculum was designed without consulting me because of the internal politics period. No, I want to record it on. I want to base it on record. That's why I'm talking. Because educated people are supposed to behave honestly, but that is not prevailing in the department. Okay, so the person concerned, at that time, who was the head of the department, that gentleman and the another coordinator whom he appointed, okay, they have not consulted me. Although my B.Tech degree is civil and structural, M.Tech degree is structural, I worked in structural divisions of NIT Warangal, and I worked in the structural engineering research center, that too in structural dynamics laboratory as scientist. But these people, because of the politics prevailing, they have not consulted me in the development of the curriculum. It was developed and the course started. Later I came to know how to teach seismic resistant design of structures without teaching structural dynamics. It is not in order, wrong. I sent mail to all the faculties. I pointed out after just they started the first batch of structural engineering. Immediately they realized and they immediately changed one of the electives and put the structural dynamics parallelly. 3 years this trend continued. Seismic resistant design of structures and structural dynamics were taught parallelly for 3 years. Now again this anomaly has happened. I don't know why. Although I pointed out to the coordinator, I already mentioned this is wrong. It's very experts happen to see, they feel it wrong. That I told. But they are least bothered. The people concerned least bothered. Only once I told her, Okay, that is one. Okay, leave it. I leave it to them. Okay, if you come across any real experts, if they happen to see your mark list, they immediately they will realize that the anomaly exists in your mark list. It's not in order because this semester you are studying seismic and studies of factors. Next semester, the department is going to offer you structural dynamics. It's wrong. It's not in order. I want to place it on record here. Okay. Next, I will go to the another discussion. The next unit, which is significance of confinement. Just few minutes. I will finish up. Okay. Just time. Yeah. Still 10 minutes or more. No problem. I want to start the next PPT. It takes time. I hope you are seeing my PPT. It's okay. Right. Okay. Right. Yeah. Significance of confinement in earthquake safe construction. Right? It was prepared long back by me, some 10 years back. Please, all of you listen. This PPT I prepared 15 years back. Whether you believe it or not, 15 years back. That time I was a senior lecturer in civil engineering. Okay. That time I prepared it. Right. This and all I already see. Concrete has several advantages. High capacity strength, availability of ingredients at reasonable cost, moldability to any shape, high resistance to fire and weathering action. Although in spite of its several advantages, concrete also has disadvantages like low tensile strength and poor ductility. Okay, the low tensile strength of concrete is overcome by provision of reinforcement by embedding steel bar inside. Okay, we call it as a reinforcement concrete, RCC. Okay, good. But how to overcome this poor ductility of concrete? What is the disadvantage of poor ductility of concrete? How to overcome it? How it helps in earthquake resistant design? Let us see the further discussion. See, what is meant by ductility? You know, you take a chalk. If you bend it, it breaks easily. Okay, it's a brittle material. All right. So I have drawn for a specific curve for a maybe elongation and force elongation curve for a brittle material. Okay. Suppose if it's a ductile, you take steel pin. If you bend it, back and forth motion is possible. It will not break easily. We call it as ductility. Okay, ductile material. In a ductile material, if you apply force, the elongation of the bar will be like your mild steel. Initially, it follows Hooke's law. Stress is proportional to strain within the elastic limit. Afterwards, it shows the phenomenon of yielding, then the phenomenon of strain hardening, and ultimate strain, and then breaking strain. So, likewise, you are getting beautiful stress strain curve. Okay, material like mild steel. That's why we can say material mild steel is a very good ductile material. The best example for ductile material is our mild steel. Okay, very good, because the amount of inelastic strain is the measure of ductility. The amount of inelastic strain is the measure of ductility. It's okay, very good, because it's undergo large inelastic deformation. See, the inelastic deformation is it undergoes large inelastic deformation without losing its strength. Okay, that is the measure of its ductility. It's okay. Next, just I want to show you. Please, all of you listen. This PPT I have prepared by downloading various collected various sources from abroad sources, international sources. That is why sometimes the unit may not be an SI unit, slightly it may differ. No problem. However, the SI unit is given in this side. Refer this side. Newton normal square SI unit 20, 40, 60, 80. Okay. Higher the grade, see the material is more brittle. I have a concrete cylinder in which a strain gauge is placed or a compressor meter you have fitted and you are monitoring the strain. If you plot the curve, see at a point 0.02, mostly the curves are at a peak. Okay, at the point 0.35, concrete with the low grade concrete fails. Okay, at the point 0.03, failure strain. Medium grade, say M20 concrete fails somewhere here. If higher the grade, high strength concrete, the descending portion immediately falls down. It's not showing appreciable inelastic strain here. Okay, at least here some inelastic strain is there up to 0.035. For this, the failure strain is even 0.003. Okay, so higher the grade, more brittle. Higher the grade of concrete, more brittle will be the concrete. That's what I want to say. Higher the grade of concrete, more brittle will be the concrete. Keep it in mind. Okay. Time also I will mark. Okay. Right. Time is there still. Right. That's what I want to tell you. Next one. See here. Stress-strain relationship for steel. You know. This is stress-strain curve for steel. Okay. Steel can undergo even strain up to not to even 0.2. It fails at 0.2. It is for a simple thing. It's drawn. Okay, then it's not necessary for you. It's okay. Actually, moving to poor ductility of concrete, the following disadvantages were felt. Please see here. I have a nice collection which was prepared for some expert lecture. Okay, so you need not go through all this point in the exemption point of view. But however, you should know. Okay, what is required for exemption point of view, I will tell you. Moving to poor ductility of concrete, the following disadvantages were felt. The concrete structure is subject to dynamic forces such as earthquakes and blast forces fail without giving sufficient warning as they are not able to absorb strain energy as efficiently as steel structures. Even under seismic loads, intermediate concrete structures fails prematurely before the ultimate load is reached. Even under static loads, indeterminate concrete structures fails prematurely before the ultimate load is reached. The reason is, it fails prematurely means proper redistribution of moment is not taking place. The moments have to be redistributed in the frame. Then only it will fail. You can avoid, you can minimize the premature failure of the frame, especially indeterminate frame. Okay, how do you improve this redistribution of moment? By improving the rotation capacity of the hinges or beam column joints. In other words, beam column joints. The rotation capacity of beam. See, I am talking in a high level, a more research level manner that you may not understand or follow. No problem. Okay, I will proceed further. Stresses due to foundation settlements, accidental overloads, and volume changes of concrete cannot be accommodated effectively, and high strength steel cannot be economically used. These are the disadvantages felt due to poor ductility of concrete. Okay, how to overcome them? I will just read out this one. For majority of hostel buildings, the most important seismic requirement is prevention of collapse and hence loss of life. For this, the structure should have specified level of lateral load resistance while capable of accommodating significant ductility demand imposed by the severe ground shaking without fracture. In addition to this fundamental requirement, the structure should also possess adequate strength and stiffness in order to limit the damage during moderate earthquakes, which may occur more frequently. Therefore, for a building to qualify as a good earthquake-resistant structure, you should have adequate strength and stiffness to limit the non-structural damage and have requisite ductility at ultimate load to ensure survival. Reinforced concrete is made of concrete which is inherently brittle. Steel not only gives adequate tensile strength to a concrete, but also make the composite behave in a ductile manner. Hence, a study of the behavior of concrete, steel, and reinforced concrete under monotonic, cyclic, and reversed cyclic load is important. Some discussion, something will go into your mind. Okay, don't worry. You will not write all these points during exam. You need not worry. Just for your information, I am telling. Slightly in a high level, more than your at research level, I will be discussing these points and all I collected. Yes, research-oriented points. It's okay. I think all this discussion may not be necessary for you. Actually, I will tell you ductility concrete. The ductility of concrete is being improved at the present by confining it in steel binders as ties in compression members and as stirrups in beams. The concrete confined in such a way is called concrete. It's not necessary. How do we achieve ductility in the concrete structures now? By confining it as ties in compression member and as stirrups in beams. Okay, that's what. Confinement. Concrete confined by providing closely spaced spirals, rectangular helical or stirrups so as to restrain it in direction perpendicular to the applied compressive stress in the compression zone of a beam. Okay, this is not necessary. See, this confinement produces a triaxial state of stress in the compression zone of the beam. That's what I will tell you. How do you plot stress strain curve for concrete? You cast a concrete cylinder and apply load in the uniaxial direction. Okay, no direction. Say x-axis direction, axis of the cylinder. Okay, that is called uniaxial loading. When you apply load in uniaxial loading, how do this failure mode takes place? First, the concrete cylinder deforms elastically. Thereafter, it deforms plastically. Okay, crushed. It means crushed. That time, the cylinder dilation of cylinder takes place. In other words, the concretes are pushed laterally. Okay, thus the fracture mechanism takes place. How do this fracture mechanism takes place? You ask me, please, I have to go even deep into the research. Even before loading the concrete, there are micro cracks present in the concrete, where at the transition zone, you know what is transition zone? At a macro level, if you see a concrete, it has only aggregate zone and hydrated cement phase zone. If you view it through an electronics microscope, we call it as microstructure. Okay, if you view it, you can see another phase. Apart from aggregate phase and a hydrated cement based phase, there is another phase present in concrete. We call it as transition zone. Okay, in the transition zone, micro cracks are present due to the porous structure of it. We have more formation of heterogate crystals, and calcium hydroxide crystals are there in that thin external plate calcium hydroxide crystals, and larger needle type of heterogate crystals are there. Due to this, this makes the framework weaker for us. That's why the transition zone is the weaker link in that concrete. Okay. In that, there are micro cracks present even before loading the concrete. Those micro cracks, when you load the concrete, at more than when the load level reaches more than 30% of its ultimate stress level, when the stress in the concrete reaches more than 30% of the ultimate stress level, what happens? This micro cracks which are present in the transition zone propagates and widen and lengthwise and size-wise. Okay, they propagate and cracks are also formed in the matrix, and they go and join with the cracks formed in the matrix. This way, the fracture mechanism takes place. Okay, this discussion are not necessary. I'm just discussing in a more research level out of my self-interest, curiosity. It's okay. I will go to the next discussion. What is that? The next one. Okay, that's what that much not necessary. Just listen here. A time just a few minutes. So the time, yeah, another 5 minutes. I have to stop. Another 5 minutes. Right. Confinement by spirals or hoops. This is the confinement. Okay, by spirals or hoops. Right. Confinement reinforcement. When you confine the concrete, what happens? See here. This. You take a rectangular column. I have provided the lateral ties like this. Okay, when the concrete is loaded in the axial direction, it tends to dilate. Okay, it tends to dilate. That time what will happen? This link will bend. This link will bend. Only the corner it offers confinement pressure. The corner reinforcement will provide more confinement pressure, while this cannot, because this will tends to bend like this, like a ring. Later only the confined pressure. But if a circular ring, the confined pressure will be uniform. Okay, when the concrete tends to dilate, okay, or when it is pushed laterally, the concrete, the laterals provided will offer very good confinement pressure, uniform confinement pressure like this. But in the rectangular stirrups, it is not the case. Only at the corners, the confinement pressure is more. At other places, the confinement pressure is less. It's not uniformly distributed. No problem. See, this is the typical failure mode of concrete in compression. When you test cylinders in laboratory, concrete cylinders, first vertical cracks are formed like this. The fracture mechanism takes place like this, and then fails. But a cubic, in India we use a cubic string. If you test cube in one, this kind of diagonal cracks forms, and then the cube fails. Okay, right. I will do one thing. I will stop with this. Next class I will continue. Okay. I hope this much is sufficient. Just wait for a few minutes because I want to record your name for attendance. Okay, I want to record your name for attendance. Few minutes. I want to record all your name because it is the video is being recorded. So your name also getting recorded. Just I am scoring your name. Thus I am recording your name, whoever attending. I am so happy. All the 26 are attending, including me. Okay. We all are full present. Very good. Very sincere student. Right? So I am so happy to see you attending class online. Okay. All of you are attending. Your names are well recorded here. Okay. Everybody is attending. I think except Dhanalakshmi, all are attending, I think. Okay. Dhanalakshmi, whether any other name she is attending, I don't know. Just 26. Because I minus 2 no, 2 connection no, 26, just now one left. It's okay, no problem, no problem. She also attending? No problem, no problem, doesn't matter, nothing wrong. Just for record purpose, it's not, yeah, printing, right. We will record it. We will discuss. First, I will stop recording, and then if you want to discuss anything, we will discuss. Okay. First, let me to stop recording. Yeah, bye to all of you. Wait. Bye to all of you. I will stop recording. Then we will discuss if anything to be discussed.